Yep. Okay.
Hello, we are OpenBMP controller team. And what's the main use cases for our solution? At first, safety comes space. Second is create off-box programmable route policies. And after all, custom path selection algorithm. Our team was a collaboration of 7 people from different companies such as Facebook, Cisco, Google, Facebook, Microsoft, and Clarkson University. Here's a photo of our team and what we did on next slides.
All right, so let me sort of introduce what we were trying to do in the first place. I guess one of the major use cases that a lot of people would have understood from OpenBMP, at least when it comes to monitoring the BGP protocol, is that yes, you can get a lot of data on how the BGP protocol in itself is performing and a lot of other use cases associated with it. But we wanted to take that data coming in to be actually able to effectively glean out a subset of the functionality of BGP into a separate controller. So the BGP process continues to remain on the router and handles all of the neighbors as well as the update messages as necessary. What we essentially end up doing is pushing out the adjacency in-rib of the BGP protocol and pushing it out to a separate controller so that we can actually split out all of the ribs and have access to them individually up top. Now, the way we actually do this is that on every router that we want to connect up to the controller, we have a single route policy. That single route policy prevents any routes from BGP from being installed into the local rib. So if you go ahead and do a show IP BGP, if you're on a Cisco router, you'll find that you'll have absolutely no routes there. But of course, you want to be able to maintain those routes in the global rib as necessary. So the way we do that is as we start getting the routes from OpenBMP onto the Kafka bus, we effectively subsume them into our code, which builds out the initial adjacency in rib. Now, this will happen on a per peer basis, and we can sort of scale that out. And as that happens, we push it out into a single Redis database. Now, what's essentially happening is that we're splitting up the functionalities within the BGP sort of path selection algorithm and allowing each rib to exist on its own within the database. So as it continues, we can basically use any user-defined plugin for defining what a route policy should look like. So if you've played around with any of the vendor route policies, you might have some knowledge of how the CLIs work. But in this case, you could use any programmable way of taking the JSON representation of our rib and applying your own policy to it. YAML-based, JSON-based, doesn't really matter. And once you've pushed that in, we build out the post policy rib, push it back into Redis, and have that same structure go on to create the local rib, where again, you should be able to push in your own representation of a path selection algorithm so that you can select the right paths that you want to further push out. So by splitting up the ribs and only the ribs, we allow you to not only define your own route policies and own route policy algorithms, we allow you to also do your path selection algorithms much on your own. And once the local rib is populated, the main question is, how do you get these routes now populated into the router? So that's kind of where we plug into sort of the router client code. And this in itself can be completely vendor independent. You could plug in the different APIs that you have available to be able to push the last local rib down to the global rib on the router. And bear in mind that by the time we've reached the local rib, all you're really concerned about is the admin distance, the next hop of the route, and the path that you want to program. All of the context of the BGP attributes are already taken care of in the earlier 2 ribs, so you have full control over them anyway. And we have a lot of different ways in which we could do this. So think about static routes APIs. Cool, like most of the vendors will support that. But what we've been actually, once we've been playing around with this, we realized that we needed a much more performant API so that we can do batch updates into the global rib, have a way of handling notifications back to us in case next hops go down, etc. And so The Cisco service layer API was super useful in this case. We were effectively able to have a massive amounts of route downloads happen at super high speeds and also get notifications whenever next hops went down, so that effectively we're able to mimic the operation of a normal BGP protocol stack without having to handle any of the messaging mechanisms within BGP. All we handle is the RIB, and we get all of the notifications either from OpenBMP or in this case the service layer API based on lower level constructs. And you might worry about the last RIB, which is the adjacency out RIB. Well, as long as you have a redistribute command, the controller routes effectively get populated into adjacency out RIB and get pushed out to all the routers. So you will not see anything in show IP BGP, but when you do a show IP route, you see all of the routes populated via the controller. So in a way, this allows us to scale out really well, and you can clearly articulate what sort of rules determine which routes go into the routing table, so you can reduce the amount of routes that you want in the routing table, you save TCAM space, and you have full control over how you specify the route policies. We didn't complete the entire hack yesterday. Most of it was done, but we've completed most of it now, at least for it to be usable by folks. And oh, by the way, because we already have a Redis database, you can actually use Redis to construct your own CLI if you wanted to, so that you can access the adjacency in RIB post policy or local RIB on your own while the controller is operating. So this is currently where the code is. We'll continue to work on this. There are several use cases that we've actually thought of that we can expand on. So any contributions, questions, or discussions are welcome. And in case you guys want to see a demo, come by to the Cisco booth during the Beer and Gear, and you'll actually find us showcasing this exactly there. Yeah, that sort of concludes it. For any questions, we'll be around.
Thank you.
Thanks, guys.
So this is my first time doing this, so let's see here. Oh, hey, I need to hit that button. Oh. Haha, yes. I am Nick Pappin. I work for Washington State University on the College of Agriculture, Human, and Natural Resource Sciences. And I and this team created IXmon on Sunday. So IXmon is designed to look at peering DB and find neighbors that you aren't currently peered with, and then test your adjacencies. Additionally, it will also help you find places where where two ASNs are on the same internet exchange but aren't peered. So let's just take this example of you have multiple routers all connected to an internet exchange, and what IXmon will do is from your router just send out pings to other routers on the exchange. So as you can see here, member 3 clearly has a bare connection. This may be, you're both connected directly to the same switch versus, let's say, member 1, which in the example of the 6, you're in the Weston building and that router is out in Quincy, Washington. Things that are working right now, we can source a ping from a Juniper router and we can put the results of that ping into a database. Things to do for that after today is we hope to build a way to review all of those statistics via web portal, find other peers that are on your exchange, and automatically source those pings to the other peers. And additionally, we want to add in other vendors such as Arista and Cisco. So, finding other IX locations where ASNs have equipment. let's take this example. So you have Internet Exchange 1 at the top, where ASN A and ASN B both have a router, but they don't have a peering relationship, versus Internet Exchange 2 versus Internet Exchange 3, where ASN A only has a router. So to do this, we built an interface to query Arista and Juniper routers and find neighborships. Then look at ASN peering locations from PeeringDB, and then show the locations without neighbors. Something that we would like to do afterwards is maybe make this into a web app so that you can just go out to a website and plug into ASNs and see what happens. Where to next? We have spent 7 hours on this. It is very bad code. So we want to clean it up a lot, complete our to-do list, and if anybody here has any recommendations that you would like to have put in, please come join us on GitHub, fork the repository, or just feel free to send in pull requests, or get a hold of me and I can add you to the group. So thank you very much.